Hello all. Uh, I hope all of you are healthy, and I have a strong confidence that these difficult days are going to be over soon. So today I'd like to solve an example related with the Otto cycle. But before that, this slide is from your notes. I just want to go over it. As you know, the Otto cycle, which is the cycle for our internal combustion engines, consists of 4 internally reversible processes, and the first one is the isentropic compression as you go from 1 to 2, and then constant volume heat addition, isentropic expansion from 3 to 4, and constant volume heat transfer from the air. So please take a note, take a look at these slides. So today I will solve this example. Consider a modification of the air standard Otto cycle in which the isentropic compression and expansion processes are each replaced with polytropic processes having n is equal to 1.3. The compression ratio is 9 for the modified cycle. At the beginning of compression, initial pressure is 1 bar and temperature is 300 Kelvin. Volume is 2.3 meter cube. Approximately the maximum temperature during the cycle is 2000 Kelvin. So what is asked? We are required to calculate the heat transfer and work in kilojoule for each process in the modified cycle, the thermal efficiency and the mean effective pressure in bars. So as you see, the modified cycle, the difference is, look at the process 1 to 2, it is isentropic compression, where n is going to be normally equal to 1.4, but if you have a polytropic process from 1 to 2, then it is a polytropic process with n is equal to 1.3. So that is the main difference, and it is not isentropic anymore. Okay, it is instead it is a polytropic process. So what we have air in the enclosed system. As you see here, we have air. Okay, so this is the piston in cylinder. So this is our piston. Okay, and here we have air in our control volume. So air goes through several processes, and we have both compression and expansion are polytropic with n is equal to 1.3. N is equal to 1.3. So in this case, PV to the n is constant, where n is equal to 1.3. Air is ideal gas, and we have also kinetic energy and potential energy changes are negligibly equal to 0. They're all equal to 0. So if you look at the PV diagram, we can plot it here, the PV diagram, where we have going from 1 to 2, okay, and 2 to 3, and 3 to 4, and 4 to 1. Okay, so these are the processes where we have PV, and when we look at the maximum temperature, where T3 is equal to 2000 Kelvin. And we know the compression ratio V1 is equal to V1 over V2 is equal to 9, where T1 is equal to 300 Kelvin and P1 is equal to 1 bar. Okay, so we have these, and we have polytropic compression and expansion with n is equal to 1.3, all processes are internally reversible, air behaves as an ideal gas, and kinetic energy and potential energy are negligible. So let's begin by fixing each of the four principal states. So we have T1 is equal to 300 Kelvin, and our table A22 gives us U1 as 214.07 kilojoule per kilogram. Okay, and from here we can use polytropic compression, where T2 is equal to T1 multiplied by V1 over V2, which is to the power n minus 1. So this is the polytropic equation, and if you write it, this is 300 Kelvin. V1 over V2, which is the compression ratio, the maximum volume to the minimum volume, n minus 1 is 0.3, and so we are going to get 580 Kelvin as the temperature for T2. So once we define this U2 from the table, 419.55 kilojoule per kilogram. And we know T3 is 2000 Kelvin. T3 is, we have also information about T3, which is 2000 Kelvin, and from the table U3 is equal to 1678.7 kilojoule per kilogram. And for the polytropic expansion going from 3 to 4, we can calculate T4 as T3 multiplied by V3 over V4 to the power n minus 1. And V3 over V4 is going to be equal to V1 over V2, and therefore we will get 2000, this time 1 over 9 to the power 0.3 n minus 1, and it becomes 1035 Kelvin. So corresponding U4 is going to be equal to 789.05 kilojoule per kilogram. We now determine all the states, their internal energy values and temperature, and don't forget that we are using ideal gas. And what is required, if you remember, the heat transfer and work in kilojoule for each process in the modified cycle. So we are going to calculate for each process from 1 to 2 to 3, and 3 to 4, and 4 to 1. Okay, and we know that, for example, here 1 to 2 we have both work and heat, but 2 to 3 we don't have any work, and 3 to 4 we have heat and work, but 4 to 1 we have only heat rejection. So for the first part, okay, let's start with work 1, 2 per unit mass is equal to, from 1 to 2, P dV, and this equal to R T2 minus T1 over 1 minus N. You can easily derive this, and that's going to be equal to R being 8.314 divided by molecular weight of air. So that's going to be kilojoule per kilogram Kelvin, and 580 minus 300 Kelvin divided by 1 minus 1.3, which is equal to which is equal to minus 267.9 kilojoule per kilogram. So this minus sign is automatically there and showing that it's a compression and it is a work done on the system. So if you perform an energy balance, Q12 per unit mass, U2 minus U1 plus work Q12 per unit mass. So that's going to be, we know our values, 419.55 minus 214.07 plus we are gonna use the term there, the negative sign. This time it's negative, so it is gonna be work is negative minus or plus minus 267.9 kilojoule per kilogram. So the result is going to be equal to minus 62.42 kilojoule per kilogram. So this is also negative, which means that heat is lost from the system. Work is negative and heat is also negative. Now for the process 2 to 3, let's remember here 2 to 3. So this is going to be the heat addition and work is 0. Therefore we have only heat addition, and it is going to be W23 is equal to 0, and energy balance Q23 per unit mass is going to be U3 minus U2, and that's going to be which is 1259.15 kilojoule per kilogram. So you see that it is a positive sign. And process 3 to 4, we are gonna have similar to work 1-2, process 1-2, and we are gonna use the same equation per unit mass. Mass is same. So from 3 to 4, P dV and is equal to R T4 minus T3 1 minus N. So if you plug in the values, you are going to see that this is also positive now. It is expected, and you compare it with the work term here, work 1-2. Work 1-2 is minus 267.9, and the work you get, this is the power stroke, and this is the useful work, is approximately 3 to 4 times greater than the compression work. So this is the useful work, and when you use the energy balance Q34 per unit mass is equal to U4 minus U3 plus V34 per unit mass, and the result is going to be 33.45 kilojoule per kilogram. So this is also positive. So heat is transferred to the system. And for the last process, process 4 to 1, work 4-1 is equal to 0. You see it here. Okay, so work is 0, and we have Q41 only. So work is 0, and the energy balance Q41 per unit mass is equal to U1 minus U4, and that's gonna be minus 574.94 kilojoule per kilogram. So that's also negative, and it is heat loss from the system. So we calculated everything related with the heat and work for all processes. Now the thermal efficiency, which is the desired output required input, and you see that it is the desired output we cycle per unit mass, and required input is the heat energy given to the system. Okay, so we know that we cycle per unit mass is equal to V12 plus V34 per unit mass. We already calculated those, and this is minus 267.9 plus 923.1. So this is a positive output kilojoule per kilogram. And if you look at the Q in per unit mass, it is nothing but Q23 per unit mass plus Q34 per unit mass, and that's going to be equal to, I write it with the signs, 33.45, which is 92.6 kilojoule per kilogram. So the thermal efficiency is going to be divided by, and it's going to be equal to 0.507, which is 50%. This is relatively higher when compared to actual internal combustion engines, but we know this is an idealized cycle, therefore it is expected. So mean effective pressure is calculated. Mean effective pressure, and as you know that the mean effective pressure is calculated as cycle work divided by V1 minus V2. Okay, so it is the net work of the cycle divided by the sweat volume, work obtained from the system divided by volume. So this is the work per unit volume, and it is considered to be a energy density. So the larger this value is better, so you get more work from per unit cycle. So we know the cycle work, and we can write it in this form. We cycle per unit mass divided by V1 minus V2, V1, okay, parenthesis 1 minus V2 over V1, okay, V2 over V1, which is going to be actually the compression ratio, 1 over compression ratio. So you can calculate it, you can calculate V1 as RT1 over P1, and that's going to be equal to 0.97. This is the specific gas constant multiplied by 300 Kelvin divided by 1 atmosphere is 10 to the 5 Newton per meter square. So this is 0.861 meter cube per kilogram, and the mean effective pressure is going to be 655.2 kilojoule per kilogram divided by 0.861 meter cube per kilogram, 1 minus 1 over 9, and we need to correct for the units, 10 to the 3 joule, kilojoule, and 1 over 10 to the 5 bar Newton meter square. So the result is going to be 8.56 bar. And this is the last required unknown, which is mean effective pressure. Thank you.